At this point, we can also deal with something that we refer to as piecewise functions. It's kind of like Frankenstein. We're going to use a particular piece of an overall function that we already know about, but we're only going to use it in part. We're going to use just a chunk of it. So like the Frankenstein idea, like, hey, I'm going to use a forearm here, I'm going to use an upper arm from this other body, torso. So we're kind of Frankensteining some functions together, chopping stuff up and saying, we're going to put these things together. We still have to have functions though, so there's kind of some stuff that we've got to keep track of when it comes to when we're allowed to use the different pieces, so the different parts of the domain. When are we allowed to use this piece? We've still got to maintain our function definition. And one of the ones that we're actually already aware of, but possibly not in the sense of it being a piecewise defined function, is the absolute value function. The whole idea we said originally when we first talked about absolute value was absolute value takes a number and turns it positive. And that does omit that particular case of the absolute value of 0 is still 0, but that means that if you picked a positive number, nothing happens if you turn it positive. It already is. But if you pick a negative number, then something actually happens. You turn that positive. There is an action taking place. If we pick a positive number, nothing happens, right? If we pick a positive number or 0, nothing happens to that number. But if we pick a negative number, then we have to change it into a positive. So this piecewise defined function business has the individual rules that we are using. By themselves, each of those rules is its own function, but we're only going to use part of it. The conditions tell us what part to use. Look at an example here. Let's say that we've got this function that has t as the number of years after 1970. So 1970 means t equals 0. And our function is giving us the number of vehicles in millions, like the number of vehicles sold in millions. So if we wanted to figure out how many vehicles were sold or were out there in the world in 1990, then the way that this is phrased is that there's this little twist. We don't just go plugging in 1990. This function starts with t equals 0 corresponds to the year 1970. So the year 1990, well, how many years after 1970 is that? That's 20 years. Now, with this piecewise defined function, we've got to know, first of all, if we're going to try to plug in the 20 for t, which of the two pieces are we supposed to use? So we go to those conditions. If t is greater than or equal to 0, less than or equal to 20, the or equal to 20 part of that statement, that's what we need for that year 1920. So we want this blue condition here to be used for the year 1990 because that's the t equals 20 that we're talking about. That function rule says that if we're going to be plugging in the 20 for t, that first piece says 17.5 times the 20 plus the 250. So if we crunch that out, that's going to give us 600, meaning that there were 600 million vehicles in the year 1990. So I think that instead of talking about how many were sold, we're really talking about how many are out there in the world on the road. 600 million vehicles in 1990. What about in 2009? Well, again, we got that little twist. We're not just going to plug in the 2009. We need to know how many years since 1970 would get us to 2009. So 2009 minus 1970, that's 39 years. 39 years puts us in the second condition, the green condition for that. So plugging in 39, we have to use the second piece. The second piece says 10t, and t is 39, plus 400, crunch, crunch, and that's going to give us 790. So there were 790 million vehicles in 2009. Well, that's all well and good if we're just talking about, hey, let's plug some stuff in, make sure that we can do some number crunching. But we've seen already, we do have some graphing that we might have to accomplish. So what is it that we could do to graph the piecewise defined functions? So let's take a look at that with our other example here. Let's keep things a little bit on the mellow side. And we've got an example here where the first piece is just a linear function, the second piece is also just a linear function. But if we're equipped to graph each of those individual functions, then it doesn't matter what pieces they might pick. So they could give us other kinds of functions once we get other kinds of functions under our belt. We have our conditions. So mark them green and blue. What we could do is go through and fill out a table, put that stuff together. And we're going to do that here. As you can see, got that mapped out. One of the other things that we can do as well, though, is we can use our graphing skills with those individual pieces and then say, if I draw in the full graph of each of those, cool. But the conditions tell us we're only supposed to be using those drawings in certain places. So what we could do then is say, okay, if I've drawn the entire first function and I've drawn the entire second function, what parts would need to be erased so that I am only using them based on the conditions that we've been given? So either way, you might want to approach the graphing task of graphing these piecewise defined functions. It's entirely up to you. But the most basic sort of idea behind graphing is pick numbers, plug them in, play connect the dots. Play and connect the dots, gotta be a little bit more careful when we talk about those individual pieces. So we can go through and start saying, based on that first condition, where x is greater than 1, let's say maybe we pick we pick 3, sorry, that's a little sloppy. We pick 3, we pick 2, we pick 1, but when we pick 1, we're not going to actually be allowed to have that final value. So we're going to need to be mindful about that. According to that first condition, we don't actually get to use the value of our function when x is equal to 1 that comes from the first piece. So when we calculate that out, while we are using the green first rule and condition, we're going to have to make sure that we're careful about that business. When we move to the second piece, well, we are allowed to use 1. So we'll want to know what happens there to our function, and that would be using that second piece instead, and then moving off to the left, 0, -1. So this is where we would use our second rule based on that second condition. So let's go ahead and crunch these things out. F of 3 uses the first piece, so 3 plus 1 is 4. F of 2 uses that first piece, 2 plus 1 is 3. And just so that we know how things look, if we use the first piece and plug in x equals 1, we would get a y value of 2. But we've got that marked with a red star to make sure that we're careful about how that's going to end up being used when we put our graph together. What we are legitimately allowed to plug in for the x equals 1 is when we use that second rule, and that says x minus 3. So that's actually a y value of -2. Plugging in 0, we get a y value of -3. Plugging in -1, we get a y value of -4. According to the grid that I have, our x's are going to go by 1s, and our y's are going to go by 2s. So we can now put dots in here. We'll use green dots for x equals 3, y equals 4. For x equals 2, y equals 3. And then, since this other entry is going to be special, we're going to use a red marking for that one. We'll use blue markings for the other 3 rows that we've got going on there. So let's go ahead and put these in. From the first row, x equals 3, y equals 4 means that we've got a dot like so. X equals 2, y equals 3 means that we've got a dot like so. And x equals 1, we're not allowed to plug it into the first function. So if we're not allowed to plug something in, that means that we would have an open circle. We'll put that in red, again, because we know we're not allowed to actually plug that in. That's not going to be part of this green drawing that we will make, but we do get to go all the way up to that open circle. So if we connect those dots together, the first piece, based on the conditions that we have, give us this. We call it a ray. It says, though we've taken a line and cut that line somewhere, so the ray has, loosely speaking, a starting place and continues in some direction forever and ever, in this case, up and to the right. So that takes care of that green section from the first rule and the first set of conditions. And then the blue that we're going to draw in from the other rows. The next row, when x truly is allowed to equal 1, and we plug it into the second piece of our function, then we get a dot where we do get to land. So we have a solid dot going on there. 1, -2, 0, -3, and then -1, -4. And that would continue off to the left and downward. To go back to that earlier comment, can I just graph the x plus 1, put the whole entire thing down, graph just the x minus 3, put the whole entire thing down, and then go and erase the pieces that we don't want? Yeah, absolutely. If you drew in that entire green line, If you drew in that entire blue line, that's fine. That's a great start. Draw in that green line, draw in that blue line. But then you got to go back and you got to erase certain parts of what you've drawn based on the green line only gets used if x is greater than 1. So if the green line is only going to get used when x is greater than 1, the part of that line that's over here to the left of x equals 1 gets erased. And because of that inequality, we're only supposed to be using it when x is greater than 1. We've got to put in this open circle here because we're not allowed to land on that part of that green line that we would have originally drawn in. Blue line, yeah, it goes on and on off to the right, but that second set of conditions says we really only want that blue line if x is less than or equal to 1. So we would have to erase anything off to the right of x equals 1. We do get to land on that spot, so that instead of an open circle is the solid dot. We get to land on that spot. Now, other than the absolute value, you might say to yourself, yeah, big whoop, why do I care? Well, we're bringing in a little something that is used in the real world. For any of y'all that have to pay for electricity or water service, I give you the greatest integer function. So if, let's use water as an example, if today you used 120 gallons of water between showers and flushing potties and running your sink, running your dishwasher, doing loads of laundry, let's say that you're like smack on, I used exactly 120 gallons of water. Cool. That's an integer. My bill is going to say today I used 120 gallons of water. But let's say that yesterday you used 115.2. They're not going to charge you for the 0.2. They're either going to take that reading and bump it down to the 115 or bump it up to the 116. Now, in all likelihood, you talk about the gas company, you talk about the power company, they're probably bumping that up. I would have to look at my bill and talk to the power people to know for sure. So the idea of the greatest integer is a little bit nicer. It's the friendlier version. So they're not going to charge you for the 0.2. They're going to take the biggest integer that would be smaller than the 115.2. So bump it down. Bump it down to the next or the last greatest integer. So greatest integer. So that's any time that we do not smack on have this integer number. This is something that also used to apply to phone bills back when people used to actually make long distance phone calls and they'd go, oh, you know, I was talking on the phone, I had a long distance phone call, I was on there for 63 minutes and 45 seconds. Are they going to charge me for the 63 minutes or are they going to charge me for 64? Well, we've got this piecewise defined function business that would tell us if we talked exactly for 64 minutes, no big deal. But if we talk for 63 minutes and 40 seconds, are they going to, 45 seconds I think is what I said, are they going to bump that down and charge us for 63 minutes? Or are they going to bump that up and charge us for 64 minutes? And so there's that piecewise defined function idea. This one's called the floor function because it bumps down. There is another version that is a ceiling function, and that would bump things up. If we graph things, they're going to look like a series of steps. So these are referred to as well as step functions. You're going to have a little chunk like this, and then boop, you're going to bump up to the next step. And then you're going to go boop, bump up to the next step. So each of those integer markings is going to have that flat, and then you hit the next one, boop, bump up. So you get something that looks like a set of steps. Is it bumped down? So they had me at 115.2, but they're only going to charge me for 115. Bump me down, floor. Or are they going to take my 63 minutes and 45 seconds on the phone and bump that up to 64 minutes? And that would not be a floor function. Instead, that would be something we would call a ceiling function. So we've got those sorts of things that happen, realistically speaking, to us, piecewise functions, in control of water bill, power bill, in that sort of way.